A2 and A3. Let's generate the span of these vectors. And we'll call them the span of AK. From K goes from 1 to, in this case, what's the highest index there? 3. What's the span of those vectors? So the span is going to be the set of all vectors B such that what is true? How big is B? B would be, what is the span again? As a set?
As in English or?
Both.
All right. All possible linear combinations.
Awesome.
The set of all possible linear combinations.
Awesome. And what does that mean?
That there is an infinite number of x, which is this kind multiple of x1 times n1 plus x2
Plus
plus
x3 times.
a3.
And what's the one condition on each of those things? What's the condition? Do these have to be specific? Is the span a limited set?
No.
How many vectors are in the span? A bunch, all of them. An infinite number, right? Because the span is generated by doing what? Yeah, irrational, rational, any possible real scalar, and running through every possible linear combination that can exist, right? Let's run through this specific one. So we're going to go over to that board. So if B is in the span, what does it mean for B to be in the span? If B is an element of the span of this vector, these vectors, what does that mean? Then, what do we immediately know about B? B should be able to be written as a linear combination of these vectors. We'll go ahead and introduce summation notation. So this is now x1 times 1, 1, 0, 0 plus x2, 0, 0, negative 1, negative 1 plus x3, 1, 1, 1, 1. And what would that look like? x1, x1, 0, 0 plus 0, 0, x2, x2 plus what? And what does that look like? This would be x1 plus x3, x1 plus x3, and then this one would be, look, x3 minus x2, x3 minus x2. What do you notice about that, the behavior of that vector? What must be true about everything in the span? Here's another question. Is it possible to have a vector that looks like this? Why not?
Because first and second element should be equal. Well, I cannot see third and fourth, but I assume they are not equal. Yes, they are not.
Yeah, sorry. That's you can't see the third and fourth because people's heads are not translucent, right? All right, got it. I need to go up. So, which implies, so the whole idea here is the vector 1, -1, 2, 3 is not an element of the span of these vectors. And why was that again, Anna?
Because you just showed that first and second coordinates of that vector should be the same, and the third and fourth should be the same.
Since any vector in the span of AK from K goes from 1 to N must be in the form, what does any vector look like?
X1 plus X3.
Yeah, maybe we'll call them alpha and beta for some alpha and beta element of R. What's another way to say that? What would be a vector that's in the span? Give me some vectors that for sure would be in the span of this thing. Okay. Here are some. One of them would be 1, 1, -3, -3. Give me another one. 0, 0. Give me another one. 1, 1, 1. Ooh. With that said, what do you notice about 1, 1, 1, 1? Did you need A3 in order to generate this span? A3. Sam just said something very, very interesting. Sam just said that the third vector A3 could be written of the vectors A2 and A1, which says, this is actually exactly where I wanted to go with this one, that the span of A1, A2, A3 was actually equal to what? In other words, A3 is, or was, redundant with respect to what operation? To linear combination. Another way to say that it's redundant is, what does A3 do for the span? Nothing. It adds no new information. A3 adds no new info to the span. Do you know what we call that? Is A3 independent from or dependent on A1 and A2 with respect to linear combinations? Yeah. So then we say, using an adjective, A3 is linearly dependent on A1 and A2. What does that mean about that particular vector A3? It's not needed from the standpoint of the span, but what does it mean from the standpoint of linear combinations and these two vectors? A3 is a linear combination of A1 and A2. It depends linearly on those vectors.